Hi, my name is Alexander Munoz, and I'll be solving the Laplacian equation on a rectangle today. So let's start by taking a look at the equation. This triangle here denotes the Laplacian operator. And let's evaluate that on u of x comma y and set it equal to 0. That's the Laplacian equation. Now let's take a look at the domain that we're working on. The domain is a rectangle, so it'll look like that. First, let's take a look at our left boundary here. All along this boundary, we know that x is equal to 0, if this is the origin right here, and y varies. So we can say that u of 0 comma y is equal to 0. On this right boundary here, if we set this x value equal to L, we can say the same thing with L, that u of L comma y is equal to 0. If we set the top boundary limit equal to L as well, we can say that u of x comma L is also equal to 0. And finally, for our bottom boundary here, we'll set this boundary as our function boundary. So that means that u at this boundary, which is x comma 0, is equal to some function of x. Let's call it f of x. Okay, now that we have the domain that we're working on, let's head back over here and define the Laplacian operator. So the Laplacian operator is equal to the second partial derivative with respect to x of u plus the second partial derivative with respect to y of u. And all that's equal to 0 because of the equation above. Okay, so the important part about this type of equation is the ansatz that we'll use. We're going to use the ansatz that u is a product of a function of x and a function of y. So let's denote that by saying u equals big X times big Y, where big X is a function with only x as its variable, and y is a function with only y as its variable. So now that we have that ansatz, let's plug it into our differential equation and see what we get. So we know the second partial derivative with respect to x of big X, big Y, plus the second partial derivative with respect to y of big X, big Y, is equal to 0. So from here we can differentiate because we've separated these our function u into products of x and y. So for example, for this first term here, we're differentiating with respect to x. So we can hold y as a constant and just differentiate x. We'll get x, big X, double prime, times y, which was held as a constant. Doing a similar thing for this next term gives us x as a constant times our second derivative of y. And all that is equal to 0. So the next step we're going to do here is divide both sides by big X times big Y. We can do that because we set u equal to big X times big Y. So if either of these were equal to 0, that would mean that u is equal to 0, and then we're just solving the trivial equation of 0 equals 0. But we're looking for non-trivial solutions right now. So it's safe to say that we can divide by x and y because they're not equal to 0. So let's do that. So dividing by big X times big Y on this term, and by big X times big Y on this term. Over here, the y's will cancel, and over here, the x's will cancel. So we're left with the equation big X double prime over big X plus big Y double prime over big Y is equal to 0. So on this left side here, in this circle right here, we have an equation that's only in terms of x. Everything here only has x as its variable. on this right circle here, we have an equation that's only in terms of y. So, and we know that these two sum to 0. So an equation in terms of x and an equation in terms of y can only sum to 0 if they're both constants. You can't have x plus y equals 0, for example. So we know these will both be equal to constants. So let's set this right circle, y double prime over y, equal to alpha squared. And let's set this left circle, big X double prime over big X, equals negative alpha squared. So now we've generated two equations. One of them is big X double prime over big X equals negative alpha squared. Let's start by solving that. That equation can also be written as big X double prime equals negative alpha squared big X. This equation should remind you of an equation we saw earlier, y double prime equals negative lambda squared y. So we know the solutions to this were sines and cosines, so we can apply the same thing here. Big X must be equal to a sine alpha x plus b cosine alpha x. Also worth noting is that we have to take the square root of these alpha squareds to get to alpha in this equation here below. So we could have set both of these equations up here equal to alpha, but we would have had square roots in our answer here. So setting them equal to alpha squared just makes this look cleaner and simpler, so that's why we did that. So let's move on to our equation for y now. We have y, big Y, double prime, equals alpha squared big Y. So this should remind you of the equation we saw earlier, which was y equals lambda squared y. We saw that last module, and we know the solutions to this are hyperbolic sine and cosine. But we'll denote them by saying big Y is equal to c e to the alpha x, to the alpha y, excuse me, plus d e to the negative alpha y, which is just equivalent to a sum of hyperbolic sine and cosine. So now we have two equations for big X and big Y in terms of some eigenvalue alpha. So we want to solve for this eigenvalue alpha by using our boundary conditions. Let's start by using this boundary condition here. This says that u of 0, comma y equals 0. So what exactly does that mean? Let's take a look. U of 0, comma y is equal to big X of 0 times big Y of y. And all that is equal to 0 by the boundary condition. However, we know that big Y of y cannot always be equal to 0 because that would make u equal to 0 and make the equation trivial once again. So from that we can conclude that big X of 0 must be equal to 0. So let's plug in 0 for x in the equation for big X that we generated down here. Plugging in x for the arguments of sine and cosine give us a times sine of 0, which is 0, so this term will vanish. And b times cosine of 0, well cosine of 0 is 1, so this will just be b. We had some practice solving those earlier, so that just gives us x of 0 equals b, which is equal to 0. From this we can conclude, because b is equal to 0, this term will vanish and we're left with big X equals a sine alpha x. Okay, so we've used this boundary condition here to solve for a meaningful conclusion. Now let's move on to our next boundary condition. Let's try this one here, which is u of L comma y equals 0. That looks similar to the one we just used, so let's just apply the same methodology. X sub L must be equal to 0 for the same reasons I mentioned up here. And so let's plug in L for x in the equation for big X that we just generated in the step before. Doing that yields A sine alpha L. So right now we're trying to solve for alphas that will make A sine alpha L equal to 0. We know that the eigenvalue solution, alpha n, for that equation is just n pi over L. So now we've made a meaningful conclusion from this boundary value, actually finding the eigenvalue for these equations. So we can now plug in that alpha for the x and y that we generated earlier. Let's do that here. Big X is equal to A sine of alpha x, but alpha equals n pi over L. So this is just n pi over L x. Big Y is equal to c e to the alpha y plus d e to the alpha y. Let's plug in n pi over L for alpha. We get c e to the n pi over L y plus d e to the negative n pi over L y. So now that we've used this boundary condition, let's move on to our next boundary condition, which is u of x comma L equals 0. So for the same reasons I've mentioned before, that implies that y of L is equal to 0. So let's plug in L for y here and see what we get. We get c e to the n pi plus d e to the negative n pi. And all this is equal to 0. But what we want to do right now is we want to actually solve for d, so that we can plug d, what we solve for d in terms of c, back into this equation up here. So let's try that. Subtracting c e to the n pi from both sides gives us d e to the negative n pi equals negative c e to the n pi. Then we're going to multiply by e to the n pi on both sides to get just an equation in terms of d, which is d equals negative c e to the 2n pi. So now let's plug that in up here in our equation for big Y. Big Y is equal to c e to the n pi over L y plus d is negative c e to the 2n pi. So I'll make this a minus c e to the 2n pi times e to the negative n pi over Ly. So we can just subtract n pi over Ly using our exponent rules. Okay, so we're almost done. We have an equation for y and an equation for x. Let's combine those together and see what we get. U, we know, is the product of big X, big Y. So we have a constant A and a constant C here. And here's, let me just box these here to make them more visible. So we have a constant A and a C. And when we multiply them together, we can just put those together as one constant. But keep in mind that that constant can vary based on the value of n we input. So we'll denote that constant a sub n. Now we can multiply these, just finish multiplying these two equations. We have sine n pi over L x times the rest of this here, which is e to the n pi over Ly minus e to the 2n pi minus n pi over Ly. Now, an important step is that we're missing a sigma here. And that's because the solution to this u is actually the infinite sum of these linearly independent solutions that we've generated. So we have to include each n in our solution for u. So from here, the only thing we're missing is an, a solution for a sub n. And we're going to generate that by using our last boundary condition, which is u of x comma 0 equals f of x. So let's plug that in and see what we get. We'll have u of x comma 0 equals, so we're plugging in 0 for y. We're going to get the sum n equals 0 to infinity a to the n sine n pi over Lx. Plugging in 0 here, we get 1. Plugging in 0 here, we'll get e to the 2n pi. And we know all of this is equal to f of x by our boundary condition. So from here, this should look shockingly familiar to our Fourier series expansion in terms of eigenfunctions. So we're going to use the same rule to solve for our a sub n's. And that's the rule using inner products. So a sub n is equal to the inner product of our function f of x times our eigenfunction, which is sine n pi over Lx, over our eigenfunction, the inner product of an eigenfunction in itself. So that's sine n pi over Lx, comma, sine n pi over Lx. So solving this equation here, we also need to multiply by 1 over this term right here that we're excluding, so that's 1 over 1 minus e to the 2n pi. Okay, so now solving this here, we'll, just using some integrals, which will vary depending on f of x, will give you an equation for a sub n. We can plug that expression for a sub n back into our expression up here, our equation here. And that'll give us a final solution for u that satisfies every boundary condition. Now there's one more thing to address, that it was kind of convenient that there was only one boundary condition here that included a term f of x. So what would we do if, let's say, this was f of x and this boundary condition here was g of x? So for that type of situation, we'd repeat the process we just did, assuming this was 0. And then we'd repeat the process here, assuming this was 0, this was g of x. So we would have to, or we can only do one boundary condition that is a function at a time and set the rest equal to 0. So in that case, we would solve for a u sub 1 that we just found, plus, let's say, a u sub 2, where f of x was equal to 0 and g of x was now non-zero. And our final solution to this overall equation, u, is just a sum of our u1 and u2. So that's how you solve the Laplacian equation on a rectangle. Thank you for watching.